Hello everyone, welcome to lecture 2 of week 8 of the course Power Network Analysis, in which we are continuing our discussion on the third last module, which is power flow analysis. And in this discussion, we'll understand the first general method of solving power flow equations, which we call as Gauss-Seidel method. In the previous lecture, we have seen at length the nature of the power flow equations, and in order to have consistency between the number of power flow equations and the number of power flow variables, which are bus voltage magnitude and phase angles at all buses in polar coordinate version, or the real and imaginary parts of bus voltage phasor for all buses in rectangular version. That for in order to have that consistency in number of equations and number of unknowns, we also have understood the reason for classification of buses into PQ buses, PV buses, and slack bus, the three major categories in which the buses need to be categorized so that power flow equation become solvable. So what we understood in the previous lecture that the power flow equations are nonlinear equations. In fact, when we choose polar version of coordinates for voltage phasors, the power flow equations have transcendental terms. What are these transcendental terms? Each power flow equation would have a term which would consist of a form of this order: sine theta k minus theta I, or vi vk mod cos of theta k minus theta I, where theta k is the voltage phase angle of bus k, vk is voltage magnitude of bus k, and similar notion for bus I with respect to vi and theta I. So these terms, since they are sine and cosine functions, we call them as transcendental terms. In case the rectangular version of voltage phasors is considered, the power flow equations essentially have quadratic terms. That is, you would have terms like EI, EK, or FI, FK, or EI, FK, or uh, sort of EK, FI, and often you can also have EI square, FI square terms also present in for bus I expression. So because there are these transcendental equation terms or quadratic secondary equations, the overall power flow equations are nonlinear. They cannot be solved directly the way the circuit equations based on KCL, KVL equations which were solved, which was discussed at length in the first lecture of power flow analysis module. So since we have nonlinear equations, the usual simultaneous equations, number of equations matching number of unknowns, and simultaneous linear form of solving equations doesn't work. So far in the literature, researchers have still not been able to satisfactorily find closed form solutions of the nonlinear power flow equations. Closed form solutions, what do they mean? Closed form solutions indicate the fact that the way linear equations like Ax is equal to B, if it is a set of linear equation and A is well defined, then X can be simply obtained as A inverse of B, where A is a full rank matrix, and that's how the factor of A would come in. So this form of solution for Ax is equal to B indicates the closed form solution. The same, however, have not been satisfactorily done or achieved for nonlinear power flow equations. And these power flow equations, they have to be solved for unknown voltage phasors with known data specifications such as network parameters, network topology, both of which are obtained from parameter estimation exercise, which is part of state estimation, load and generation injections, tap positions, capacitors, etc., etc. So all those input information is known, which again we have discussed in the basis or assumptions involved in power flow. And since these are nonlinear equations, the techniques which are commonly available, they tend to be either iterative techniques or recursive techniques. And each of these techniques, they start with some good estimate or good guess of what would be these unknown voltage phasors. Without an initial guess, these iterative or recursive techniques cannot work. Now, what is the difference between iterative and recursive techniques? Just to state in a very layman perspective, iterative techniques often tend to find the values of all unknowns in one single go, whereas recursive techniques would try to find the solution of each of these unknowns at a time. We'll understand, or this difference between iteration and recursion would become clear when we discuss the Gauss-Seidel method and other iterative techniques at length. But just to summarize, iterative techniques, they try to find all unknowns, which those unknowns refer to all voltage phasors together in terms of voltage magnitude and phase angle. Iterative technique would try to find all unknowns in one single step, whereas recursive techniques, they would try to find one unknown at a time, and then with one unknown known, the second unknown would be known based on the first unknown, and that's how the phase-wise recursive process would go on. The techniques available for power flow analysis, they can be well classified into, I would say, three broad categories. The first basic one is Gauss-Seidel method, which is a recursive method. The second most common method available in textbooks at least is the Newton-Raphson method, which is an iterative technique. And from industry grade perspective or from the application perspective, the well-known technique till date used is the fast decoupled method, which is an extension of Newton-Raphson method. Of late, from the research perspective, at least a decade ago, there has been this method known as holomorphic embedded method, which is actually an extension of Gauss-Seidel method, and this method has shown computational efficiency in terms of time saving compared to Newton-Raphson method and fast decoupled method, although holomorphic embedded method has its own demerits which still have not been addressed from the research perspective satisfactorily. So from the discussion perspective, we would discuss the first three topics at length because these are well-known techniques available in different textbooks, references, and literature papers. The holomorphic embedded method is more of a research perspective technique which still needs some maturity for its actual application. And as I mentioned, most of our industry grade solvers, they are based on the fast decoupled method, which we will discuss probably in the next week discussion as the time comes in. So coming to Gauss-Seidel method, there is a uniqueness to Gauss-Seidel method. We have discussed about these power flow equations in transcendental form or second order form depending on polar or rectangular version of voltage coordinates. Coincidentally, Gauss-Seidel method does not need these transcendental or quadratic expressions. In fact, it rearranges or tries to solve the entire equation in its complex form. Remember, when we were discussing these power flow equations, I had mentioned that often these equations are segregated into real and imaginary components, specifically the complex power injection equation, from where we get real equations, and there we can try to solve for real variables where voltage magnitude and phase angle are again real variables. On the other hand, Gauss-Seidel method has this unique property that there is no need to separate out real and imaginary components of a given complex equation. It can very well handle or solve the complex equation as it is. So, Gauss-Seidel method, irrespective of voltage phasor in polar or rectangular coordinate, the entire complex power flow equation is rewritten, rearranged, and then the Gauss-Seidel method is applied to solve the entire equation together. Before we apply this Gauss-Seidel method, the classification of buses into slack, PV, PQ needs to be done a priori so that we can have consistency in terms of knowns and unknowns. So if there is an n bus network, we number those buses by as 1, 2, 3 till n. And for the sake of discussion that we will have, we will assume bus 1 to be the slack bus, which is one unique bus, and it is acting as angle reference as well as voltage reference for all other bus voltages. So we are choosing bus 1 to be the slack bus, although the the discussion would remain same. The bus numbers may be changed as per the convenience. So if I have to understand Gauss-Seidel method, let's look at what was our complex power flow injection equation. The basic complex power flow injection equation was based on the fact that the complex power at bus I, which is SI, is product of voltage phasor at bus I and the conjugate of current phasor at bus I. So if I rearrange the conjugate term, so essentially I would have SI conjugate into VI is equal to VI conjugate into II, where II can be further expanded in terms of individual Y bus elements and all N bus voltage phasors, which again can be rewritten in a fact that, so if I look at my complex power for injection and focus on the boxed terms, which are these two terms, the first box term being over here and the other one over here, I basically have to find voltage phasors which tend to satisfy this complex injection. And SI conjugate, SI is PI plus JQI, J is the complex operator, root over of -1. If I rearrange this a bit in the sense that, for example, if I focus on these two boxes, then I can rewrite the entire equation as Pi minus JQI is equal to YII VI conjugate VI plus K is equal to 1 to N YIK VI conjugate VK, where K is not equal to 1. I divide the entire equation by VI conjugate because VI conjugate is common in both these terms. So if I do that, then I have VI conjugate divided over here and the denominator. VI conjugate gets removed from here, and I take up this second term, minus it over here, and then divide the entire expression by YII. I would have this as my equation, which can be used for Gauss-Seidel method. So how does the Gauss-Seidel method work? It tries to find the latest bus voltage at bus I using the previous estimates or previous known values of remaining bus voltage phasors. It includes the information of bus I itself as well as bus K. Obviously, the Y bus elements have to be known, the network topology is known, parameters are known, and these injection values are also known. Then only this equation would become solvable, and that is where the premise of or assumptions of power flow analysis come in. So I have bus 1 as my slack bus. I can use this equation or solve this equation in a recursive manner. And before that, I have to find the initial choice or guess of all voltage phasors. So usually we choose the bus voltage to be a voltage which is practically realizable or practically achievable or practically observable. In per unit analysis or per unit system, the way we choose our base voltages and base power, it is expected that the voltage magnitude of a bus will typically be close to or around 1, because that's how the base kV has been chosen. And in fact, we were discussing about high voltage solution and low voltage solution in the previous lecture. So high voltage solution, which refers to a voltage value being around 1 per unit, is the practically realizable voltage value, and essentially that itself can serve as a good initial choice for voltages of all PQ buses. And angle values or phase angles of all bus voltage phasors with respect to the chosen reference, where we usually choose 0 degrees or 0 radians as angle reference or angle value for angle reference bus. So it's common that we can choose other phase angles also as 0 degrees. For PV buses, the voltage specified for the PV bus itself can be chosen, and it is better to choose that value because this value has been obtained as per some active power loss minimization exercise, which indicates that for the PV bus, the voltage at the terminal of a synchronous generator can be controlled by proper reactive power control or power factor control. So we call this initial choice to be a flat start. The flat term here refers to the fact that since the number of PV buses in the network would be very limited, not all buses would have generators connected to it. So comparatively or usually we would have lot of PQ buses, and for all such PQ bus we would often choose one at an angle 0 as the good initial choice for unknown voltage phasor. Since the voltage profile is all 1 with the phase angle being 0, the voltage profile itself is mostly flat, and that notion of having a flat voltage profile is associated with this flat start of initial choice. So given this classification and initial choice, now if we want to find or make use of this Gauss-Seidel technique to find the solution of this equation in a recursive manner, what would we do? Let us start. So since bus 1 we have chosen as the slack bus, its voltage value is known. For slack bus, no power flow equation needs to be solved. So exclusively for bus 1, this equation need not be solved. That means for slack bus, there is no need to solve this, because for the slack bus, the voltage itself is known. So what we would do is we would start solving this equation for the next bus onwards, which is bus number 2. So if I write the equation or expand this for bus number 2, for bus number 2, what I would observe, I would see that V2 would be equal to 1 by Y22 multiplied with P2 minus JQ2 divided by V2 conjugate minus Y21 V1 minus Y22 won't exist, so Y23 V3 goes on till Y2n Vn. And while I am trying to solve this equation, essentially I am trying to find the value on the left hand side. And this left hand side value can be known when I know the initial values of the right hand side quantities. With flat start as my initial choice of values, I very well know what is V2, V3, Vn. These need not be the final solutions. So for a kth step or for the first step, if I associate the initial choices by a superscript, let's say 0, then V1 0 doesn't make sense, because V1 refers to slack bus. Its voltage would always remain constant. So V1 doesn't need any subscript or superscript like 0 or 1 indicating the recursion number. V1 would remain fixed as it is chosen as slack bus. We know what is V3 0, Vn 0, which are essentially these initial choices that I have marked. And that is the reason why the 0 superscript is appearing there. And after I put in all these right hand side values with the known subscripts, I can solve the right hand side, and the value that I would get would be related to the first recursive value of V2. So V2 1 would indicate the first recursion value of V2 in Gauss-Seidel method. And the same would continue for V3, V4 till Vn1 has been obtained. All these voltages for all n voltages, when combined together, the way they are being solved, we are trying to solve each voltage at a time. So let me show you the next slide. So for V2, I would get V21 based on the prior values of voltages known on the right hand side. Once the first recursive value of V2 is known, I can move on to the next bus number, which is V3. And when I find V31, remember V30, it is the previous value whose initial choice has been chosen. But now if I look at V2 term, the latest value of V2 has been chosen here. That is the difference. And similarly, while for all other voltages, they are still retained at their 0th recursive value. For V41, I'll be using the latest values of V2 and V3 and not their previous values. While for other buses to come, I'll still be using the previous value. And this sort of a recursive process continues when I reach or find Vn1 eventually. When I find Vn1, I would have found voltages or first recursive voltage updates for all voltages, and hence essentially in Vn1 on the right hand side, I will not have any term with a subscript 0 sitting on top, because all voltages would have been evaluated, so subscript would become 1 for all of them. So with this, the first recursion would continue. So if in general, if I have to find the kth recursion solution for bus I, for kth recursion of bus I, for all prior voltages before bus I, which is bus number 1 to I minus 1, the latest bus voltage phasors which is to be used, which is the kth recursion itself. Whereas for following buses from I plus I to n, the kth minus 1 recursive value would be obtained, and all this is known or possible only when these injection values are known. So I'll come to that aspect a little later. To further speed up or improve the convergence property or reduce the number of recursions, accelerator factor can also be used as per this equation, where typically alpha between 1.4 to 1.5 dramatically reduces the number of recursions. And all this is true only when, as I said, the injections are known, Pi and Qi are known. For slack bus, since there is no equation involved for PV for slack bus, so there is no problem associated with Gauss-Seidel method for slack bus. For PQ bus also, these P's and Q's are known, so the same equation as it is can be used to find the voltages. For PV buses, however, there is an issue, because for PV buses, Q as such is not known explicitly. So how do we apply Gauss-Seidel method for PV bus? The next few slides would explain that specifically, because for this equation to be solved, Q has to be known and Q is not known explicitly for PV bus. So how do we do about that? As I mentioned yesterday, if for PV bus Q is not known explicitly, the best reasonable logic would be, okay, fine, we don't know what is the Q, but we definitely know for sure what are our latest voltage values for all buses. Can we not use these latest voltage values and evaluate the reactive power expression? From there we get the reactive power injection, and probably that injection value could be used in this voltage equation if PV bus remains as a PV bus. So that complexity, let's see what that complexity is. The same equation, that means the way of solving this Gauss-Seidel method, is not applicable for PV buses. So Q is not known a priori for PV buses. What do we do? Best possible way, evaluate it at the latest voltage phasor values, use the latest voltages and evaluate this expression. So CAL refers to the calculated value. For a PV bus to remain PV bus, its reactive power injection or generation should be within a minimum and maximum limit as defined by the capability curve of the synchronous generator connected to the PV bus. So using this calculated injection, we find what is the generation at the PV bus. If QG is within its limit as per the capability curve, PV bus remains as a PV bus. That means its voltage value remains fixed, the magnitude remains fixed. So how do I find the voltage magnitude remaining fixed? Doesn't essentially mean that the phase angle should not change. The phase angle can still change in the Gauss-Seidel method. So to ensure this, what we do, we directly use the Qi calculated value into this expression here, solve the right hand side, get the latest voltage update for the PV bus, and this voltage that we have obtained need not have the same voltage specification which was there for PV bus. PV bus remains a PV bus as long as Q is within a limit. If Q is within a limit, voltage magnitude should not change. So we in a way correct the voltage magnitude as per this correction factor. So this correction factor, if you see, Vi specified is the specified voltage magnitude of PV bus. We are dividing the voltage phasor by the actual value of the voltage magnitude that we have obtained and multiplying with the Vi specified value. So in a way, the phase angle between Vi corrected, COR refers to the corrected voltage magnitude. The phase angle of corrected voltage and the evaluated voltage phasor do not change, only the magnitude is changing. Now this is all good when PV remains a PV bus if this condition in blue is correct. What happens if this condition is not true? In that case, generation or generator cannot or should not generate above its maximum limit or below its minimum limit for the purpose of maintaining safety and security. So if QG is trying to violate its limit, we limit its value to the limited cap, because from the safety perspective, all excitation control is lost. So all of it has been utilized. In case QG is trying to violate the lower limit, as per this condition, we cap it to its lower value. If it is trying to violate its maximum limit, we cap it to the maximum value. Once QG value has been capped, we can now find, depending on whether the demand connected to the PV bus or not, we can find the injection at the at this bus, which is trying to become a PQ bus. For PQ bus, Q has to be known. So we tend to call this violated term because the reactor power generation has been violated. So PV is now becoming PQ. And we use this QI violated as it is over here into the Gauss-Seidel update equation, and then try to find the voltage phasor for this converted PB to PQ bus. Why does this conversion happen? Because the PV bus has lost its reactive power generation capability handling limit. PQ bus is called because the Q is now becoming specified for this converted PV to PQ bus. In such a conversion, voltage need not remain fixed. Voltage magnitude can change, so no voltage magnitude correction is required. The generator is not able to control or regulate its own terminal voltage. The terminal voltage is now being dictated by the power flows happening in the power network as per the lines which are connected to this PV to PQ converted bus. Now, once the PV bus is converted to PQ bus, it is not necessary that it should remain as a PQ bus. We always have to make a check whether this converted PV to PQ bus can come back to the PV status. For already converted PV to PQ bus, the conversion can only come back again when the PV bus has regained its capability of maintaining the terminal voltage via reactive power control or excitation control. So what we do for this converted PQ bus, we change its voltage magnitude first to the specified value, correct the value of the voltage phasor, use this voltage phasor, evaluate the expression of QI as shown over here. With the corrected voltage and this Q expression, find the reactive power generation. If this reactive power generation comes back within its limit as per the correction, then this converted PQ bus, which was actually PV, can again regain back its PV status. Once PV status has been regained, voltage magnitude remains fixed. The phase angle can change, and the phase angle can change as per the correction given in the slide number 8, which was this particular slide over here. Sorry, the slide number is wrong. This has to be slide number 10, not 8. I'll correct this when I change the slide there. And if QG doesn't remain within its limit for this converted PV to PQ bus, the status remains as PQ, and we evaluate the voltage magnitude and phase angle as per the information given on slide number 11, not slide number 9. So all this goes on when there is a check of when this all process can stop. All this process stops when the voltages do not change. The voltage changes have now saturated. So a measure of doing that is to ensure or check whether the actual injections which are being calculated, do they match their actual specifications in terms of generation and load specification. If the differences are very small, the mod infinity here refers to the infinity norm. This is the infinity norm of a vector, which in a way is also same as the maximum absolute value of a vector. This vector here is a vector sitting inside this. If the maximum absolute value of the vector is less than a particular tolerance, which is a numeric tolerance, we say that the method has converged, the solutions have now been obtained, and for different buses, the corresponding specifications, they are all defined. The same convergence can also be used for finding or for making check whether the difference in voltage magnitude of a particular bus between two recursive iterations is less than some epsilon or not. And this needs to be checked for all buses in order to ensure this convergence criteria. Before we go into the corresponding example and I conclude my discussion today, I would like to spend some time on understanding what is the nature of convergence of Gauss-Seidel method. Gauss-Seidel method can be used, it is a recursive method, but what type of convergence does it attribute? Is it linear convergence? Is it a quadratic convergence? Typically methods, numeric methods, their assessment or performance assessment is based on what type of convergence do they provide. So to do that, I'll take a very basic approach. So basically in Gauss-Seidel, what I'm trying to do, I'm trying to equate this term with respect to this term, and I'm assuming that all on the LHS, which is the first ticked box, is known. And on the right hand side, I'm trying to find these voltages which, if found, should equate these two boxes. And the same equation in Gauss-Seidel form gets rewritten in this fashion. So if I were to generalize it in terms of a recursion property, so given that at kth recursion of Gauss-Seidel method, if I write a generic equation and I choose my notation of variables to be x now, so xk plus 1, which is the term, let me write that first, xk plus 1 is in a way equal to p of xk divided by xk plus, okay, minus q of xk. What are xk plus 1 and xk? Xk plus 1 is identical to Vi k plus 1, the kth plus 1 recursive update of voltage phasor I. Pxk, small pxk, or maybe let me use a different notation. Let's say if I use Rxk and Txk. Okay, so Rxk is actually Pi minus jqi divided by Yii. Qi can also be a function of Vik. Xk itself is Vi, some form of a conjugate, and Txk is the summation term Yik Vk divided by Yii, the term sitting over here. So I can correlate or rewrite this Gauss-Seidel iterative equation into this particular form. And overall, if I see and try to equate these two boxes into a form of the nature like I want to solve for x, where g is the equation, should be equal to 0, then essentially I am trying to convert g of x into x is equal to r of x divided by x minus t of x. This is the reoriented form of the g of x expression, where g of x refers to the two equated boxes over here. And on this equation, if I apply Taylor series expansion of this equation at some initial value or some value of x is equal to xk, what do I get? I would get xk minus rxk divided by xk plus t of xk. Or maybe if I simplify this a bit, if I take Taylor series of g of x at x is equal to xk, what do I get? I would get g of xk plus first derivative of g of xk into x minus xk plus double derivative of g of xk, x minus xk square by 2 factorial, and so on. This should be equal to 0. For timing, if I assume the effect of first, second order terms to be not there, or even if I retain it, I can always rewrite this as g of xk is same as this term, which is equal to 0. So I can substitute this as x minus xk minus rxk divided by xk plus t of xk plus, so this is the term over here. Then I have x minus xk, which is the term over here, multiplied by the first derivative of g at xk, which would result in 1 minus r prime xk by xk plus r xk by xk square plus t prime xk, so on, almost equal to 0. I am neglecting the higher order terms for the sake of simplicity of our discussion. Now in this, if I look at this term here, the term sitting over here, and compare it with the Gauss-Seidel update method, this is nothing but xk minus xk plus 1. Pardon me for the subscript or superscript. Here it should be actually xk plus 1 plus x minus xk multiply, then I have plus x minus xk r xk by xk square minus r prime xk by xk plus t prime xk should be equal to 0. Xk and xk, they get cancelled here. So I have essentially the term like, and if I define error at k plus 1 recursion to be x minus xk plus 1, then the error at the kth recursion is x minus xk. So if I use that, this term here can be written as ek plus 1 plus ek multiplied by the, let's say if I use a form of the fact that, let's say if it is some wxk, where wxk is the entire term sitting over here, equal to 0, which indicates that ek plus 1 is minus wxk into ek, or indirectly ek plus 1 is proportional to ek. This proportionality in terms of the errors in the current recursion and previous recursion is responsible or indicative that the Gauss-Seidel method has linear convergence. When we discuss Newton-Raphson method, we would see that Newton-Raphson method would have ek plus 1 proportional to ek square, which would indicate that the convergence is quadratic and not linear. So basically the convergence is happening in a much more slower fashion. It's all linearly happening, whereas in the Newton-Raphson method, we would see this to be in a quadratic convergence, and quadratic convergence saves time. That is the benefit. So Gauss-Seidel method in general is recursive and has linear convergence, so it has slow convergence property. Convergence of Gauss-Seidel method becomes very difficult when the network loading is extremely high and the voltage stability or instability problem might come in those cases. Gauss-Seidel method has difficulty in convergence. Lines have high R by X ratio, specifically in distribution systems. So Gauss-Seidel method need not give you the proper high voltage solution. For networks which are highly radial and weakly missed, the way distribution systems are, Y bus tends to become very highly sparse. So basically the YII term becomes much more significantly lower compared to off-diagonal terms, and that also results to difficulty in convergence of Gauss-Seidel method. Series compensation, if it is very high, line reactance can become negative. That may also lead to problem in Gauss-Seidel convergence. We'll conclude the discussion today with an example in which we take a 3-bus network. Bus 1 is given as the angle reference bus. Bus 2 is a PQ bus. Bus 3 is a PV bus with voltage of 1.05 magnitude, and power is 1 pu at bus 3. Reactive power generation should be between -1 and +1 pu. So how do we solve Gauss-Seidel method for one recursion, choosing unknown flat stat as unknown voltages for initial guess? Since bus 1 is the angle reference bus, its voltage magnitude is given as 1 pu. We first find the Y bus for this 3-bus matrix. The 3-bus reactances, all these reactances, they are given on a common pu. So we can evaluate the Y bus, get this thing confirmed. Bus specifications as per the classifications are also known. So since bus 1 is a slack bus, so no equation needs to be solved for slack bus. We can start with bus 2 as the iterative update for bus 2 itself. So if we put in those initial values of flat stat, 1.05 pu remains same for V3 because V3 is the PV bus. Then we get the first update of voltage at bus 2 is as this complex number. When we go for bus 3, since it is a PV bus, we need to check whether its generation, which is based on the latest voltage values, is within its limit or not. The voltage, the generation value is not within its limit because maximum value is 1 pu. So we cap QG at 1 pu and recalculate the corresponding injection, which turns out to be equal to, since there is no load, so Q3 in itself becomes 1 pu. We use this 1 pu over here, find the voltage value. The magnitude is no more equal to 1.05. No correction is needed. The bus has become a PQ bus. And this process, when continues, we eventually see that after 19 recursions, the solution process converges. That means the mismatches have turned down to 0. And voltage of V2 and V3 as per this order, where V3 bus 3 is still not a PV bus. In the next discussion, we will take up our next technique popular technique known as Newton-Raphson method with application for voltages in polar coordinate. And we'll try to understand this more in terms of example. Thank you.